Hi, in this video we're going to talk about dilations to y. Well, what is a dilation? Well, a dilation is when you're going to multiply y by some value. So if you can multiply it by a value between 0 and 1, or you can multiply it by a value that's greater than 1. So in that case, you'd get a fraction, like 1/2, or in this case, you get a whole number, like 2. Okay, so we're going to be looking at both of those cases. But I'm going to erase this so that I'll have enough room to write on my graph, because I don't want those numbers getting confused with what we're doing. Okay. All right, so let's look at the first one. We have y equals 4x. Well, what kind of function is this? Well, we can see that it's linear. Well, what does a linear parent function look like? It looks like y equals x. So if that's the case, then 4 is actually been multiplied to y. So actually we're multiplying the result of x, which is y, to 4. So therefore, this is going to be a vertical change. So for the y values, when you multiply or dilate them, you just multiply the value by whatever the y values are. And so this is going to be a vertical stretch. Okay, so let's see what that looks like. Well, if we graph the line y equals x, it looks something like this. We still have our 1-to-1 ratio passing through the origin, with a slope of 1 to 1. So this is our linear parent function y equals x. Well, now what we want to do is graph our dilation. So what we're going to do is take the values of what they were before. So for instance, if y was 1, 2, 3, 4, let's see what's going to happen to those values. Well, if I take the y value of 1, so at this level we're changing the y's, and I multiply that by 4, well, that's going to become 4. So notice that for y, you do whatever it tells you to do. There's no need to switch like you do in the x values when you're trying to do dilations for x. All right, so if y is 2, then you multiply by 4, it's going to become 8. And so you get something like that. If y is -1, it's going to become -4. If y is -2, it's going to become -8. And so what you get is a line that has been vertically stretched up. So assuming I can draw it perfectly. So it's a line that's been vertically stretched up. So it now has a slope, instead of a slope of 1, it has a slope of 4. Okay, so this one is y equals x, and this one is y equals 4x. So it looks steeper, yes, but what's happening is it's actually vertically stretched. So you should be using those terms. So it's vertically stretched by a factor of 4. Okay, that's very important. Okay, so now let's look at another type of function. In this case, we have y is equal to 1/4 x squared. Well, that x squared tells us that this is a quadratic function. So let me go back to my other color. This is a quadratic function. And we know that a quadratic parent function is y equals x squared. Well, in front of that x squared, right? So if the parent function is x squared, then the 1/4 is actually being multiplied by y to y. So that 1/4 is going to do something to our function. And so for vertical, so when something is being directly applied to y, the 1/4 is actually going to do exactly what it says. Well, if we divide something by 4, it's going to shrink vertically. Okay, so it's not like x where you do the opposite. For y, you do exactly what it says. So it's going to shrink vertically by a factor of 1/4. Okay, so let's graph the parent function. We know that it's 0 squared is 0, 1 squared is 1, 2 squared is 4, -1 squared is 1, -2 squared is 4. Okay, so there's our parabola, and this is y equals x squared. Okay, so I'm going to zoom in now so we can see what's happening when we graph our transformation. Okay, so if it's telling me to take y and multiply it by 1/4, it's really telling me to take what my y values are. So if they're 1, 2, 3, 4, 5, 6, 7 on, and so on, it's really just telling me to take those values and divide them by 4. So if y is 0 and you divide it by 4, it's going to stay 0. So that point doesn't change. If y is 4 and you divide it by 4, it's now going to become 1. If y is 4 and you divide it by 4, it's now going to become 1. If y is 16 and you divide it by 4, right, then it's going to become 4. Or if y is 3 and you divide it by 4, it's going to become 3/4. But we can see what these points are doing. So that's going to help us because we don't really have a reference for the other points. But we can see that our function is going to be stretched out. I mean, will shrink. It looks stretched out, but it's actually shrinking vertically. So it looks like the values have been compressed down. So if you'd like to use the word compress, shrink, whichever is your fancy. But just make sure you understand what's going on with the y's and you can describe that. Okay, so let's look at this function here, y equals 1/2 3 to the x. Well, we can see that this is an exponential function, and so we look at the base, and our base is 3, and our exponent is x. So this has a parent function of y equals 3 to the x. So the 1/2 is actually the dilation that's going with y. So if y is equal to 3 to the x, then once we find 3 to the x, that gives us y, and so we're going to take half of it. Okay, so how does that happen, and what is that going to do? Well, we know that when we multiply y by a fraction, or some value that's between 0 and 1, right, then it's going to shrink. And because it's applying to y, it's in the vertical direction. So it's going to shrink, or it's going to shrink vertically by a factor of 1/2. So that means we're going to take all the y values and divide by 2. So let's graph the parent function first. 3 to the negative 2 is 1/9. 3 to the negative 1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 to the second is 9. And so our function looks like this. All right, and approaching 0 at the asymptote. So y is equal to 3 to the x. Okay, so now let's graph the transformation, or the dilation. So we're going to take each y value. So if our y values are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then we can take whatever the y value is, and we're going to multiply that by 1/2 or divide it by 2, which is the same thing. So if y is 9, it's now going to become 4.5. So that will be down here. If y is 3, it's going to become 1.5. If y is 1, it's going to become 1/2. If y is 1/3, it's going to become half of that. So 1/3 times 1/2 is 1/6. So that's going to become even smaller. And then if y is 1/9, so for these small points, multiply that by 1/2, it's going to become 1/18. So that's even smaller than what it was before. So when we connect these points, we see we have a new function that has shrank vertically. So it's been compressed vertically. And so we can see that it's compressing in to be closer to the x-axis, right? These values are getting closer to 0, and then these values are shrinking. They're getting closer to the x-axis as well. All right, so that is for the exponential when you multiply it by a fraction. Let's look at another case. So in this function, and let me clear the space so I'll have some room, we have yet another exponential because it's 2 raised to the power of x. So we use the base that we're given. Y is equal to 2 to the x is the parent function, and this one is exponential. Okay, so this 3 is the dilation that's being applied. If y is 2 to the x, and then we multiply it by 3, then that's going to stretch our y value. So it's going to stretch vertically by a factor of 3. So whatever the y value is, it's now going to be 3 times that. So let's graph the parent function first. So it's y equals 2 to the x. So if you're struggling with the exponent rules, right? If x and y, if x is negative 2, then y will be 1/4. If x is negative 1, then y will be 1/2. If x is 0, y will be 1. If x is 1, y will be 2. And if x is 2, y will be 4. Okay, so you should remember those. It's okay for you to write them down for now, but you shouldn't have to do those every time. You need to remember your laws of exponent rules when applying those negative exponents. Okay, so let's graph this one. So to the -2, it's 1/4. To the -1, it's 1/2. To the 0, it's 1. To the 1, it's 2. And to the 2, it's 4. And if we want to even include another point, then we can include 2 to the 3 to the third power, which would be 8. Okay, so we get a function that looks like this. Okay, not quite as steep if you compare this parent function to the other parent function. They look very similar, but this one is a little more rounded. It's a little wider than 3 to the x. Okay, so now let's graph the transformation. So we're going to take whatever the y value was, and we're going to multiply it by 3. So for this one, right, we didn't really have to put this point, but if y is 8 at this place, then if we multiply it by 3, that'll be 24, so we can't really graph that one. But now let's look here. So this is 1, 2, 3, 4, so this is at level 4, and if we multiply it by 3, it's going to now be at 12, so we could actually extend it. Our graph only goes up to 10, but we can add 2 lines, and so we know that this value would be here. If our value is at 2, 2 times 3 is 6, so that value will be there. And then if our value is at 1 times 3, then now that value will be there. And then if we multiply 1/2 times 3, that's going to be 3/2, which is 1.5. So the new y value will be there. So notice that the x values are not changing for any of the y's. They're all staying the same. And so let's try the last one, 1/4 times 3. That'll be 3/4, which is 0.75. And so that will be just below 1. Okay, so when we graph these new values, we can see that this function, it appears to be a little bit steeper, but what really happened is it was stretched. Okay, so it's like it's being pulled up, like somebody is pulling it up with one hand and they're pulling it up vertically, and so it's kind of losing its curvature. So it looks like it's going up straight, like it's getting steeper, and you could say that, but that's not how you describe the transformation. The transformation is that the y values are actually tripling, and so the function will appear to be steeper. All right, so I hope this video has helped, and I will see you in the next video.